Fine. So now we all are live. Okay, so students, in yesterday's class, what are the things which we have studied? Let me tell you, the time is, we have waited a lot for other students to join, okay? So now we'll start it. And one thing you understand, what's the one thing which you must understand? See, understand this thing. That yesterday what we did, okay? First of all, we revised that thing, yesterday's thing. Yeah? So good evening to all the students who are in the class and who haven't joined. If maybe they are in the YouTube, okay, yes, YouTube students, fine, okay. Okay, by the way, let me see somewhat on the YouTube also, what is happening there. So this is Avanti Live 13. And if I see the students, are there any students on the YouTube present? Or it's like Live 13 and here we go. Yes. Okay. So in the previous class, what we studied? In the previous class, we have studied this topic, that is interference. Okay? In the previous class, we studied interference. So now let us see the contents of that part. I mean, yesterday's class. In the yesterday's class, we have have gone through the introduction to interference. We've gone through different kind of sources, that it coherent and incoherent sources. Then we have gone through a topic which is known as superposition of light waves. Then at the last, we have gone through this thing, that is Young's double slit experiment. Why double slit? Because single slit, it is something like a gap narrow between a cardboard, and double slit looks like this. That is dual gaps. Dun, dun, dun. Okay. So then we have seen this animation so many times. I will launch it for the last and the final time now for the revision part. So the pattern due to both of the sources light, which you will be able to observe on the screen, will be what? Will be what? Interference pattern. Okay. And then we have seen the definitions of this and some equations. These equations, we have seen two conditions which are required for interference throughout this chapter. We remembered in the previous class. What was these? Okay. So GNV students have joined. I hope my voice is today clear. There is no any issue. If still students you find any issue, please, we are requested to give the feedback here only now. Okay. So that we can correct it just at the moment when you may feel like it's, voice is not clear. Okay, that's fine. Very good. So we have seen the two very important strict conditions for what? We have seen two very important strict conditions so that we can observe the interference pattern. Okay, it's okay, very good. So we can observe the interference pattern. The first condition is this: the waves must be monochromatic. This now it must have single wavelength, and sources are coherent. Then we understood a difference between the coherent source. Just by picture, we can guess back all the theory. And next is what? Incoherent source, this switch. Okay. Also, we have seen a theory that for incoherent source or incoherent light, the frequency is not constant. Also, the phase difference is not fixed. Everything is random. So you can see it, how the waves are very unsymmetric with amplitude, frequencies, omegas, and everything. Then this example we have seen where a polychromatic light gets converted at ultimately after this on the most, it starts from the polychromatic most left hand side and ends at the what kind of coherent monochromatic. On the most right hand side, coherent monochromatic on the most right hand side. Then we have seen this question and we got the answer at the end by making a chart. CHART wala chart, not that. That B14 is that answer. Why? Which will show the interference pattern 24/7. 24/7 per like 24 hours, 7 days, continuously forever working. So this is what I mean. The question was which among these pairs will show the interference. So this can only be predicted if we check the frequencies. Frequencies here are all like same only. There is not a lot of issue. Next thing we need is what? Phase difference angle. So that we get from here. Okay. So phi here is this. This one is omega 1 minus omega t. This is time dependent. If we check for 2 and 3, this is answer. This is again time dependent. If we check for D3 and 4, this is again time dependent. But only B14 is the answer. Like it's B14, which is time independent. Remember it, okay? So if we see the phase difference, see, this was the formula, phi 1 of 1 minus phi 2. Okay. So if you check the phase difference here, this is coming as time independent. Then we've seen the real theory and seen some pictures also. Net amplitude is big, y1 plus y2. Then we've seen the mathematical equations. You know, all these are mathematical equations. And the last, we have derived this equation of interfered wave. When the two waves have superposed, their interfered equation is this. Okay, where capital A gives you this value. Then we have seen the condition for constructive interference. Okay, and the angles for these we have seen the phi must be, if you're finding the phi to be these values, then it is brighter spot. And then destructive interference condition we have seen, like this. So for destructive interference, if the angles are 2 and 1 plus pi, it means odd multiples of pi, you will get what intensity to be 0 there. Power difference given is this. So for constructive interference, power difference is n lambda. Constructive. For destructive interference, power difference is 2n1 plus lambda by 2. So wherever you find this power differences, you must guess from that only. You must be able to know this. This will be of the brighter spot, and this will be of dark spot. Okay. Then it was given a picture. See, we were having two pictures. One for the constructive interference, another for the destructive interference. Okay. So for the constructive interference, I hope I'm audible. Yes. So for the constructive interference, we have seen this. What was the picture is. But for destructive, it will be not maximum, but y equals to y2. See, the formula we have to use the same here. Okay. What I'm saying, I hope you understand what I'm saying. The formula which we are using will be same here. But here, if you see, y1 is positive. See, it's like with the signs we have to use, maybe plus y-axis and negative y-axis. You can see here, y1 is positive A, y2 is negative A. So both the things when will get added up will give you A minus A equals to 0. Okay, that's why we are getting here a straight line. And we see here, this is a simple picture which shows you, this is actually, see, this is interference of waves again. By this picture, you can actually revise it. Okay, you can do what? You can do the revision. Suppose you're having this S1 source and you're having this S2 source. So when the light waves are going like this, and when they interfere at the point, you get like this, either the dark band, either the bright band, either the bright band, dark band, bright band. Okay. So the central band is here. Central band here is the bright band maxima. Then comes the dark band. Then comes the bright band. Then comes the dark again and the bright again. Okay, these are all the things here. Bright spot, dark spot, bright spot, dark spot, and bright spot. Okay. What's the Young's double slit experiment? So it's like this. Suppose you're having a source of light. This is what? A source of light. Suppose the light rays are passing from a slit like this. Suppose the light rays are passing from a slit, okay? Next, there is another double slit there, okay? So light rays are passing from that also, see, suppose. Now, in front of that double slit, there is a screen at d distance. Understand what I'm saying, okay? So this is a single slit here, this is a double slit here, and this is a screen at d distance. And this experiment shows us this. See, this is just an animation experiment. By animation, we are like trying to explain you know, but it's true here. What is happening? Suppose this slide is like incoherent. This we have seen in previous class. It's just a revision now. Our today's goal of studying is like different. I mean, today what we want to achieve, the contents, I'll show you after this, okay? Suppose we are having incoherent. Suppose we are having incoherent light source here, okay? And the light rays are passing from this like this. So see this, it's sure. See, this will not show interference because we know the strict condition for interference is coherent must be the source. Source must be the coherent. So for this to be converted first into this kind of mechanism has been implemented in between. That is, first the light rays are being passed from a single slit, okay? Then they pass from a double slit there, okay? And then you see on the picture this kind of thing. That is central maximum, then a dark band, brighter, brighter, dark band, brighter, brighter. So this is all about the experiment here.
Until then,
Yeah.
you don't connect to this one.
Hey, is anybody having any doubt? You can ask.
Switch is not on, it's not charging. Oh, power is
Are
not
you
there
having any
now.
doubt? Okay,
See that
then
breaker.
Anand, please mute yourself. Then you, then the Ara, mute yourself. Then Chitraduga, mute. Okay, that's fine now. I think I'm audible. Suppose you are having a source of light. This is what a source of light. Okay. And from these sources of light, the light rays are going out. So they will meet here on the screen at a point, say P. Okay. So we have founded the power difference, which was coming as something, okay, but ultimately we have to find the formula of the y locations of maxima and minima. This we have seen in the previous class. You know? So we got the formula and then the conditions we applied that for the brighter fringes, that is bright bluish color or yellow color, whatever, can be given by this formula. Okay. And N0 will give you the central maximum. This is the location of starting from Y0 is the central maxima. See, it's bright. No, that's why I'm saying central maxima. This is central maxima. This is position of first maxima. This is the position of second maxima. And on the next side, we can see this dark fringes. This will give you the location of N0 will give you first minima, dark spot, dark band. This will give you second minima. This will give you third minima. Okay. So through this, we can get this thing is central maxima will be at this position first. Then first minima will be at this position like this. Then again comes the first maxima. I will be this. And comes the first minima. No, second minimum actually. It will be this like this. So like this, the band picture will be understood. So these are brighter and the rest are dark. Okay. I hope this thing is now clear to you. Revision points these are. Then after this, we have seen again this something known as fringe width, which is constant both for the destructive and constructive interference of the waves or superposition. Okay. At last, I told you this thing. If they ask you in the exam, remember this point, it's very important. If they ask you in the exam, what is the fringe width proportionality? You say fringe width is proportional to distance of the screen from the sources and also the wavelength of light, but it's proportional to or inversely proportional to distance between the slits. Distance between the slits here. Okay, you just focus here. If we talk about the distribution of intensity, okay, so intensity zero goes at here. This is y equals to zero will be the intensity will be zero here. Okay, you know. So this y equals to zero will be intensity zero. Okay. So as we progress towards positive y axis and we progress towards the negative y axis in both the directions, see the graph of the intensity will be this. Why? Because these points which you're able to see here, this will give you, these are the points of max intensity. It means bright spot. Okay. And these minimas which you're able to see here, these are dark bands. These are bright bands and these are dark band. This is just a paper pen representation, the graphical representation of what we are able to observe on the screen. Okay. Remember, students, one thing, this graph you can draw for ideal condition like this. But for practical condition, actually, on the screen, the bright spots gets fade away with the distance from the central maximum. So the graph will be like this for experimental condition. This is just an ideal condition. This is the real condition. For the real, the graph will be somewhat like this. You may find like this. That is the intensity of the brighter spots decreases with the distance from the central maximum. Okay. I hope this is clear. Is the voice clear, students? Please reply in the chat box. If anybody is facing any issue in the voice clarity, so please reply here. I hope it's audible properly. Hai? I hope it's audible. So please reply in the chat box. Because now we're going to start a new chapter. We'll study now diffraction. But before that, let us see some numericals. Are you ready for the numerical? Text yes or no in the chat box. Just this numerical, okay? So see, the question is this. See, we will do combined numericals in the end of the class, but for now, just see this. Two slits in Young's double slit experiment are illuminated by two different lamps, emitted light of the same wavelength. Okay. Will you observe the interference pattern they're asking? Let us see. Okay, our answer is what? No. What's the reason? Because if they are different lampstands, they can't be coherent. They will be incoherent. And this we know is a strict condition for the interference process. What is the strict condition for interference process? That the light waves must be coherent. Okay. Yeah, this one more question we'll do, students. Numericals are also important. So this one more question we'll do. Okay, try it yourself and then reply in the chat box. Are you able to solve it? Let me give you the hint. Let me give you the hint here, okay? So it said like this, in a Young's experiment of interference of light, slits are 0.2 centimeter apart, okay? So when we say 0.2 centimeter apart, students, it means like this, that small d is given to you 0.2 centimeter, okay, are illuminated by yellow light whose lambda is given to you. So this is the wavelength of the light given to you, students. This is the wavelength of the light given to you, okay. What would be the fringe width on a screen placed 1 meter from the plane of the slits? They're telling you what will be the fringe width on a screen placed 1 meter from the plane of the slits. Simple. See, fringe width, I told you the formula of the fringe width is what? It's lambda capital D by small d. This we have seen, no? See, it is same. It is constant for both the constructive interference. It is constant for both the constructive interference. Also, it is same for the destructive interference. Okay. कंस्ट्रक्टिव के लिए भी सेम है, डिस्ट्रक्टिव के लिए भी सेम. So we can find here the beta is equals to how much? 0.3 millimeter. Okay, this is our answer. Put the values. No, everything is given in the question. See this, D is given to you. I'm like showing you with this shade of circle. Okay, lambda is given to you. Capital D is given to you, 1 meter. Put all the values here. You'll get the fringe width answer, 0.3 millimeter, and that's your answer is. Okay, fine. So students, now you want know more numericals or start a new chapter? Our revision numericals are completed, but I am asking from you, now you want more numericals or you want me to start a new chapter, that is diffraction or diffraction. Some pronounce it as like diffraction. So you have to reply in the chat box, otherwise I'll start directly. Okay. Reply in the chat box, please. You want more numericals on this, or at the end of the class we can do, I mean, when the chapter gets finished? Okay, let us start a new thing now. Okay. We are already having less classes. So now we'll start directly this thing, that is diffraction. I hope it's on your screens properly. Okay. So now it's time to start a very new chapter, diffraction. Not a new chapter, by the way. I'm sorry. It's a part of this chapter only. That is wave optics. Okay, wave optics. We started with introduction to this, Huygens theory. We have seen Huygens theory. Then we have seen what? This is Huygens theory. Next what? Anything else? Yes, we have seen interference. Okay, now it's time to see this thing, that is diffraction. Interference, maybe there were many subtopics, Young's double slit, single slit, coherent, incoherent, all this we have revised now. Okay, so now it's time to start the new thing, that is diffraction. So students, please write this thing in your notes. It's important now because we are starting new here. It's fresh thing. Please make the notes proper. Okay. Students, please make the proper notes. Now this is the new thing we are starting here. Contents, diffraction. Some say diffraction. I'll say deflection. Okay. This is new. Please make the notes proper notes. It's very important. Okay. It's an easy chapter. When next time you will see the notes, all the things will be revised in a very less time and it will be very convenient for you. Okay, that's fine. So this is, students, the contents of today's class. That is, first of all, we'll go through the introduction to diffraction. This is the first point. And second point is this, we'll see diffraction pattern. As we have seen the interference pattern, we'll see the diffraction pattern. Okay. Then third is this, we'll understand the difference between diffraction and interference. What is the difference between diffraction and interference? We'll understand. Then the fourth point is this, we'll go through the resolution of optical instruments. We'll understand this. What do you mean by the resolution of optical instruments? Okay. So I hope you have written. I'm giving you 1 minute to write all these 4 points on your notes. Okay. Then we'll start with the first. That is, what is the first point? Any one of you? First is this, that is introduction to diffraction. This will start now. Okay. So please note all these contents in your notebook so that we can start it. This is the second last, and the last chapter is polarization. I mean, last topic or subtopic of this main chapter, which is having the topic like wave optics. We'll end after that. Okay. The chapter will be completed. So please write these things. So at least we can complete 50%, you know. I'm giving you 1 minute. Okay. So let us see the introduction part. Hold on. Okay, write the contents. I'm giving you time. Okay. Hello. Yeah. Written the contents. I hope students you have written the contents. Okay. Suppose students. Yeah, you can see here. This is what? What is this? This is a source of light. Okay. And this is suppose an obstacle here. This is what an obstacle. See, this is new topic, diffraction. So now don't include or mix up, do some mashup or let me mixing up of things like of interference. Okay. Don't mix the previous concepts in this new concept, okay, which we are going to understand now. So this, you know, is what? Diffraction. Suppose this is a source of light here. And you can see here, from this source of light, the light rays are passing like this. Okay. So you can understand this. This is what an obstacle. So we are able to understand this when it is passing via an obstacle. This portion is not getting illuminated. Okay. And due to this, there is a dark spot in the middle part. And these parts are brighter. I'm writing with B. These parts are brighter, B. And this is a big dark here. Okay. This XY is a region of diffraction. Remember this? Bending of light around the corners and encroachment of light within the geometrical shadow of the opaque obstacles is called diffraction. I repeat it. Bending of light around the corners. You're understanding this? These are the bending of light. Okay. I mean, light must go like this, but it's bending. This is the regions of diffraction. And the definition says like this: bending of light around the corners and encroachment of light. Encroachment means this stoppage of light, okay, the blockage of light within the geometrical shadow of the opaque obstacle is called diffraction here, okay. Simple definition is this. See, diffraction is what? Bending of light. Understand like this. What is diffraction? It's the bending or turning of light around the corners of an obstacle. Simple is diffraction. Now, let us see this thing. Suppose see, now we are going to understand here that how there is a bending of light or how the light bends around the corners. Okay. Suppose a kind of planar wavefronts are generated. Somehow the planar wavefronts are generated. Okay. So when these wavefronts will pass through these kind of obstacles, these are the obstacles here. You can see the results. What are the results? These are the results here, okay? So when they will pass through these obstacles, these are the results here. You'll get on the screen. On the right hand side, it's able to see. Okay, now let us see a big thing here. Now I'm going to launch animation. Please watch it very, very, very carefully. Okay. So this experiment will give you a deep understanding of this topic, that is diffraction. Till now, we were seeing some refreshing points so that we can understand the main concept thoroughly, properly. But now you'll see this thing, that this animation will give you a dive and a deep dive understanding. Okay, like of this topic of diffraction. So watch it carefully. I told you already, So I'm launching it. See this. So this is a narrow slit, students, on the screen. And now I turn the cardboard. Okay. On the left hand side, you can see now what will happen. Okay. Left from the left hand side, these planar wavefronts are coming. Suppose light rays are coming. So from while passing from this source, okay, this is like a source of a narrow slit is there. On the right hand side, it will show you what, like a spherical wavefronts will get generated. So this is how from a planar wavefronts, the spherical wavefronts have been generated, and on the screen on the right hand side, you're able to observe this pattern, and this is known as diffraction pattern. Okay, although the waves are interfering, no, but still it is a diffraction pattern. See this, how the rays are going. Okay, let us see one. This is all the as we have seen the interference video. This is a diffraction video. You can see isme the width of the central maxima and the other bright spots are reducing. Okay, so intensity also gets reduced, as you will see now. Watch the video again. Watch again. Back again. Okay. So I hope that you are able to observe on the right screen, the rightmost screen, you're able to observe the pattern there. Okay, the dark and the bright band. Okay, it's clear, no? Okay, that's fine. You see, students here, these are two slits. Not a slit, by the way. This is the block. There's some kind of kind of structure which blocks, which are like a hindrance in the path of light. If I put a source of light here, this will be acting as a hindrance. These things will act as a hindrance on the path of the light. Okay. So constructive interference and destructive interference. We'll see now. So red points are the points of constructive interference, and blacky points, or the black points, are the points of destructive interference. Like this is for the dark band. This is for the bright spots or the bright bands. Okay. You can see on the left hand side on the screen, this is the dark band. This is again a dark band. This is a dark band. This is again a dark. This is dark, dark again, dark again, dark again. This is bright. This is bright, 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 bright. Okay. So we'll understand now part difference in a single slit. Suppose you're putting a single slit. This is having a gap in between it. And if suppose a plane wavefront comes from the left hand side and pass through the slit, so on the other side, you'll see a pattern like this. Okay. So actually, what is this? In this, there is some derivation. As we have seen in the interference, no, we have derived the formula of y equals to n lambda capital D by D for constructive interference, and y equals to 2n1 plus, sorry, y equals to 2n1 plus lambda by 2 capital D by D for destructive interference. Na? Similarly, we'll also derive a formula for this. And for this, we need the part difference first. Part difference is coming A sin theta, where A is what? A is the distance between the slit. A is the distance between slit. Now we'll see for the bright fringes. Okay, suppose we are going to observe the central maxima or the central bright fringe. So for that, if you focus here, see this. It's written here at the central point O on the screen, the angle theta is 0. And we know the part difference which we are getting here equals to A sin theta. Okay. And if theta here is like 0, so we'll get sine 0 angle as what? What is equals to 0 here. So A into 0 will give you what result? 0 again. So there's the part differences. Okay. So if the part differences are 0, it since all the parts of the slit contribute in phase. Phase matlab, they are in phase matlab, suppose this is a wave, and if this wave gets superposed or interfere with a wave which is having the same symmetric configuration, so you'll get a net big wave here like this. That is A plus A will give you 2A amplitude wave. Okay. That is the maximum intensity by the way. So in phase will give you max intensity. Now we'll see the location of dark fringes, students. Let us see the location of dark fringe. So you must understand this. The part difference between the rays LM. Suppose this is a ray L and this is M. Okay. Again, we'll find the part difference and we'll find the condition of dark fringe. For destructive interference, see, this is nothing but now we're taking the distance that is only A by 2. Okay. So A by 2. See, on the PDF, you all people will be given the derivation. No need to worry for that. The main thing is this: understand the formula, like remember the formulas and have a little bit of the understanding so that when you can switch, like when you switch back to the PDF, it's very clear to you. Okay. PDF will be available on your notes link. Check it out. Okay. So this is the condition. You can also write here A to sin theta, no issues. Plus minus lambda by 2. It will give you again A sin theta plus minus lambda. So for the condition for destructive will be this. That is, you will get the minima at lambda by A. See the top, hold on. Let me show you here. This is the condition for minima, n plus minus n lambda by A. Okay, and maxima ki condition kya if you focus there? Maxima condition is okay. It's just A sin theta there. Okay, I mean they haven't given the condition. The phase difference to be angle theta. Central maxima will be 0. And sine 0 it will be the central maxima. Now we are seeing first minima location of dark fringes. So for that we can put the angle to be like this. That is, see, focus it carefully. So for destructive interference, we'll put this. Why we're writing it 8 by 2 theta? The reason is this: A by 2. Actually, it is like this: A by 2 sin theta plus minus lambda by 2 is the condition for dark fringes. Okay. You have to just remember the formula. Don't worry for what's the derivation. That is available on the PDF. If you read it, if you find it's difficult, then you can call me or text me on the WhatsApp. We'll resolve it. Okay, I'll solve your issue. So the sine theta, students, when theta is very small, sine theta is approximately equals to, voice is clear? No. When sine theta is very small, I mean, when theta is very, very small, sine theta is approximately equals to theta only. Remember it. Okay. So that's why they've directly written here A by 2 theta. Okay. So through this, we'll get a formula for dark fringes. So see, students, if you put here theta equals, this is theta plus minus lambda by A will give you the first minima. Suppose this is the brighter spot, this will be the first minima. And this is a general formula for theta angle. Okay, that if you put n1, n2, n3, you will get what? You will get consecutive. Okay, I mean, you will get side by side different minimas starting from n1. and 1 will give you lambda by a, and 2 will give you plus minus 2 lambda by a, and 3 will give you plus minus 3 lambda by a. That is different minimas. Location for bright fringes are this. Again, you'll use the same formula, but you will change something, that is this. Now there is a problem in this. What is the problem? We know that central will be maximum for theta 0. So we'll say, why it's a by 3 written there? Because why cannot we tell why is the a by 3? Because central wala is already maximum at theta 0. Okay. So for the bright fringe, if you see here, answers you will get in this format, plus 3 minus 2 by lambda by a. Remember these, okay? For the bright fringe, if you'll see, this will be your conditions for maxima. So students, let us revise it again. Let me tell you, for the next class, we'll come on the diffraction. But for now, understand this. Okay, let us go to the video. What's happening here? Then we'll solve some questions on interference again, because I told you in the last, before leaving the class, we'll solve again interference numericals. Suppose on the right hand side, there is a screen, and from the left hand side, the wavefronts, the planar wavefronts are coming. And when they pass through this, you will find on the other side, what is this? A band will be formed. This is known as diffraction band. Okay. I hope it's clear. That's fine. And then we have seen now today what we have seen, that it looks like very familiar to the interference, but there is a difference in that intensity goes on decreasing. The bright spot intensity goes decreasing. And then we have seen the central bright condition somewhat. The next class I'll explain you full. It was just an overview now. And this is a condition for destructive interference, that is minima, and condition for maxima is this on the screen. Okay, that is maxima. Central के लिए theta 0 है, but for next theta, that is plus minus 3 by 2 lambda by and minus 3 by 2 lambda by is like this. This is one bright spot and this is another bright spot. Okay. So now students, let us go through the interference questions again, because now it's time to end the class. Yes, interference. Yes. So we were here. This is also one simple question, students. Please solve it. I'm giving this question as a like class illustration. We have to solve it now. Okay. This is as a class illustration. Take it as a class illustration. Class illustration. Okay. Try to solve it. Don't worry. Diffraction we have seen an overview. It's enough for tomorrow's again starting it again properly. I'm properly matlab, doing the derivations. Okay. For now, it's enough. So keep those information in your mind. That will be like acting like a tool to derive the complete diffraction equations. Okay. But now we have to practice again interference questions, because just by practicing 2 questions will not work. Okay, so try to solve it. This is a class illustration, students. Please try to solve it. This is class illustration. Okay, I'll give you some hint. Okay. See, if you focus here, just hold on. See there carefully. Okay. The above is the maximum intensity. This YDAC stands for Young's double slit experiment. This YDAC stands for Young's double slit experiment. I know is the maximum intensity given here. Okay. And they say find the intensity at a point on the screen where path difference between the 2 interfering beams is pi by 3. I mean, they're giving path difference equals to pi by 3 for 2 waves. And then for the path difference, lambda by 4. See, students, you must know the formula for that. What was the formula? We know the general equation is this, where I max is equals to I naught according to the question. Okay. देखा है ना ये formula and interference? Yes, we have seen this when we were seeing the condition for constructive interference and the condition for destructive interference. I max is I naught, maximum intensity. Okay. We know for phi equals to pi by 3. This is the phi equals to pi by 3. Okay. This is what I equals to I naught cos square pi by 3 by 2. This will give you result equals to how much? Pi by 6 matlab, see, pi by 3 kitna hota hai? What is pi by 3? Remember, this is under the cos, so this is direct angle. Pi by 3 kitna hota hai? It's 60 degree. Okay. Then pi by 6 will be how much? 30 degree. Cos 30 is how much? Root 3 by 2. Cos square 30 is how much? 3 by 4. Okay. So you will multiply like this. That is cos square pi by 6 equals to I naught 3 I naught by 4 is the answer. Okay. You'll get this value as the answer. See this. You got it? So first question ka answer is this. That is for the phase difference equals to pi by 3. The answer will be I equals to 3 by 4 I naught. And that is solved now. B ka we say this is lambda by 4 given, students. So there is, phase difference was given initially, but now the power difference is given. I mean, it's a phase difference, sorry. But now the power difference is given lambda by 4. For this, we have to solve like this. We know that K delta X, that is the power difference, is equals to phase difference. K is equals to 2 pi by lambda. Power difference is the power difference. Phase difference is what? Pi by 3. Pi and pi will cancel. So power difference you will get as lambda by 6 here. Okay. Power difference you will get as what? Lambda by 6. Is it right? It's fine, no? So now let us take it out. So we'll put this. Hold on. 1 second, students. 1 second. We don't need it. We need the phase difference. Okay. Actually, one of the students texted maybe. So we have here the power difference lambda by 4. We need the angle difference. Why angle difference? Because we can only put this angle in the cos format. Okay. So K is already 2 pi by lambda by 4. Lambda cancels. Del phi you will get as pi by 2 here. Okay. So you will put pi by 2 here directly. Cos pi by 2 is how much, students? It's 0. Remember it. Okay. So from this you'll get cos pi by 2 value as 0. Now let us see the next this question. This may B part. First is solved already. Okay. We get the answer as intensity will be I naught 3 by 4. Second is the B part, students. Okay. B part says this. So from this we can see that power difference is this. So we can find the phase difference by the formula. Wave number into power difference equals to the angular difference. That is the phase difference. K is the wave number which is given by 2 pi by lambda format. Here again the formula is printed for your notes. And when you will put this again, this phase difference we can find from the power difference, which is pi by 2 put here in this formula, which will give you, which is a general equation of intensity. Okay. Variable with the phase difference angles. So you will get the intensity to be equals to how much it is. देखो कितना है. I value I'm getting here what? It's equals to I naught by 2. ठीक है? Is it clear? I hope the value is clear. I value is equals to I naught by 2. ठीक है? So students, that was all about today's class. I hope this much is enough. Okay, we'll meet in the next class. But before leaving, please take this question as a homework. So this is again based on, so today based on interference, we did 4 questions. Okay, and now this is the 5th question for you people, and we have seen an overview of diffraction. properly we have seen the introduction, but formulas we have seen. In the next class tomorrow, we'll see the derivations, proper thoroughly derivations and some numericals. Okay. So today our interference is completed properly with the numericals. Okay. If anybody want more numericals, you can text me in the chat box or on the WhatsApp or call me if you want the modules. Okay. Whatever. You'll see, you people, if you're participating, we are ready to help. But if you're not participating in, like, the studies are not one-sided. You also have to work hard. Then only you will crack this ITG. Got it? See, now this is a homework for you. First maxima and fifth minima of the double slit YDSE, Young's double slit experiment, is 7 millimeter, and the slits are separated by this. Screen is this. Find the wavelength of the used light. So formulas you have to use simple. Okay. We know the condition of maxima. Condition of maxima is given by N lambda capital D by D. Condition of minima is given by, this is a max condition, bright spot condition. Minima condition is given by what? It's given by 2n1 plus lambda by 2 capital D by D. D is the distance of the screen from the slits. Small d is the distance between the slits. Okay. And you have to find the wavelength of light. So what do you need to do? So just put the values. First maxima, you have to put a particular fixed number with respect to the first maxima. And with respect to fifth minima, you have to put the number corresponding to that. And then you have to subtract these two. Okay. And then put it equals to 7 millimeter. Then you will get the lambda. So this is the hint which I have given to you. Please use this hint and solve it and come in the next class. Okay. Okay. So that is all about today's class, students. We'll meet in the next class. If anybody is facing any doubt, please ask. So please, if you're having any doubt, you can please reply in the chat box or yeah, that's fine. So we are going to end the class now. Students, now we're going to end the class. Okay, thank you for your participation. Bye-bye, everyone. So bye all the YouTube students and also these like JNV Chitra Durga students, JNV Lapakshi and JNV RR students. Bye everyone. We'll meet in the next class with diffraction topic properly. Okay, I mean, we'll see after the introduction, we'll see thorough derivation again, numericals. But this numerical will be provided to you on your PDF. Check out the notes. Okay, and the next class, the next week maybe we'll meet again. I'll ask you how you solved it. And if anybody is having any doubt, please reply on this number. This is for your, like, this is like a helpline number. I mean, if you're facing any doubt in physics, you want the modules, you want the material, and you're stuck in some questions, some concepts, or some counseling is required, please ask, reach us out. Okay. See, if you are not asking, then how I'll be able to know few people are stuck here? Just coming in the class and going like this, it's not like a, it's not like a game. Simple. You have to work hard, take it serious. Okay. So bye everyone. Best of luck for your test, like pre-board is coming maybe, and we'll see what to do for the online class then. Okay. That's fine. Bye bye everyone.